If you've learned about imaginary and complex numbers, you might have been asked to graph them. Typically, we do this in the same way that we plot xy points. Here is the complex number 4 plus 3i, plotted in the usual way. We go over 4 on the real axis, up 3 in the imaginary axis direction, and place our dot. But there is another way to look at it if we put the numbers in what is called trigonometric form. To locate the point, we can use the radius, measured from the origin to the point, and the angle. This is the same concept as plotting points in polar coordinates. It turns out that there are advantages to viewing the numbers this way. For one thing, it actually makes some sense of the results of multiplying complex numbers. If you recall, to multiply two complex numbers, like 1 plus 2i and negative 3 plus I, we algebraically FOIL them out, simplify the I squared to negative 1, and combine like terms. The result is negative 5 minus 5i, which seems kind of random. Let's look at all three numbers on a graph. Again, this may all look pretty random. Is there any visual relationship going on between these numbers? There is if we think in terms of radius and angle for each one. Here are the radius lengths for each point. Notice that root 5 times root 10 is root 50, or 5 root 2. The radius of negative 5 minus 5i is actually the multiplication of the radii of the other two. Next, notice what happens when we take a copy of the first angle and shift it to follow the second angle. We arrive at the angle of negative 5 minus 5i. It appears that the angle for negative 5 minus 5i is the sum of the other two. So now we've seen that when you multiply two complex numbers, their radii multiply and their angles add. Taking powers of a complex number is just repeated multiplications, so we have a similar relationship. If we want, say, the fourth power of the complex number shown here, with radius 2 and angle 50 degrees, the angle will add 4 times for a total of 200 degrees. You can think of the resulting angle as winding around the axes 4 times farther than what we started with. The radius will multiply by itself 4 times, so it will stretch to a length of 2 to the 4th power, namely 16. Unfortunately, that is going to go right off the screen, but you get the idea. Similarly, if we wanted the 10th power of this complex number, we take the 10th power of the radius and multiply the angle by 10. That means our new angle is 500 degrees, which is more than 1 complete revolution. That is perfectly fine. Our resulting angle will land in the same location as 140 degrees. The new radius is 1024. Yeah, that's not going to quite fit here. And that brings us to roots. Finding a root of a number is the reverse of computing a power, so let's see if we can go backwards. As an example, let's find the cube roots of I. Notice I use the plural roots. What's up with that? Hold that thought for a moment. Figuring out roots algebraically is not easy, but using trig form makes it quite intuitive. We can observe that the number I has radius 1 and angle 90 degrees. Consider a generic complex number with radius r and angle theta. If it is to be a cube root of I, then when we take its third power, we should get I. That means we need r cubed to match 1, the radius of I. So r must be 1 for our number also. In addition, we need 3 times our angle to match 90 degrees, so our angle must be 30 degrees. We found it. If we plot this point, we can check that it works correctly. The radius cubed will be 1, and if we wind the angle around 3 times farther, we land right where we need to be. So we're done, right? Not so fast. With real numbers, there is only one cube root. That's true. But with complex numbers, there are other possibilities. We saw earlier that when computing powers, the resulting angle could wind more than one revolution. What if that's the case here? Suppose we have a candidate number for a cube root, and when we verify it by taking the third power of it, it winds past one revolution and then lands correctly. That means after the third power was taken, the resulting angle was 450 degrees. Working backward, that means before computing the third power of it, the angle must have been a third of 450, which is 150 degrees. Now we have a second root. Are there more? Suppose a candidate number landed correctly after completing 2 full revolutions. It would have wound through 810 degrees. Working backward, it must have started with an angle of 810 divided by 3, namely 270 degrees. So we found a third one. How long will this go on? If we try a candidate number that lands correctly after 3 full revolutions, it corresponds to 1,170 degrees. Dividing by 3, this takes us back to 390 degrees, which is the same location as 30 degrees from our first root. So now we are repeating ourselves, and 3 is all there is. If we plot all 3 roots together, you'll see the symmetry. They all have the same radius, and their angles are equally distributed around a circle, with spacing 120 degrees, coming from 360 divided by 3. If you investigate other roots of complex numbers, you'll see that there are always 2 square roots, 3 cube roots, 4 fourth roots, 5 fifth roots, and so on. Now that you see the pattern, watch how fast we can determine these. Let's say we want the fifth roots of -32. We know there are 5 of them. -32 has radius 32 just by observation, so the radius for all of our roots will be the fifth root of 32, which is 2. The angle for -32 is 180 degrees, and our first root must be 180 degrees divided by 5, which is 36 degrees. All 5 roots are equally spaced around a circle, so the spacing must be 360 degrees divided by 5, which is 72 degrees. Keep adding 72 degrees to our initial angle, which was 36, and we'll get all 5.